Yeah, thanks for the organizers for the invitation and for putting together a nice program, which I noticed has a lot of sort of back-to-back theory experiments. So we go from like mind-blowing ideas to a chance to sit back and look at pictures. So that's what I'll try to provide. Okay, so my talk is called Atoms Interlinked by Light, Programmable Interactions and Entanglement for Sensing and Simulation. And broadly, it's about experiments we do in my group where we use light to mediate non-local interactions between cold atoms, particularly clouds of cold atoms, and most of what I'll talk about today. And broadly speaking, our motivation comes from a number of different directions. So one is the field of quantum metrology, where actually having sort of many atoms talk to a single mode of light is an efficient means of scalably entangling, can be hundreds of thousands of atoms. An interesting direction is to ask to what extent, in the spirit of this workshop, can one go from towards increasingly kind of programmable entangled states that might have applications to some more sophisticated sensing tasks than have been explored in the past. Another sort of broad motivation in the area of quantum computation is if one has access to non-local connectivity, that can be an ingredient, for example, for having kind of either hardware-efficient encodings of a problem or hardware-efficient error-correcting codes. And then in quantum simulation, it can sort of expand the class of models that we can readily simulate. So that might be exploring sort of exotic models of quantum gravity that require non-local connectivity, or even sort of in a more down-to-earth vein of simulations of condensed matter. Having non-local interactions can, for example, stabilize spin-liquid states in principle. And so these are all kind of directions we'd love to be able to explore in the lab. And there's actually a couple of different paradigms for sort of going beyond local connectivity in the quantum systems that are being built in various labs around the world today. And roughly speaking, I would say there's kind of two paradigms. One is sort of have local interactions, but move your atoms or your ions around. And then the other one, which you already heard some about from Crystal this morning, is have some connectivity that's global, that can be global mediated. In our case, it'll be by a single mode of light, but it could also be ions linked by their collective motion. And then the question is, can you kind of, in this top-down way, also have a programmable quantum system? And Crystal's talk introduced you to this idea in the setting of trapped ions. So this method on the left is definitely very powerful, particularly for sort of building up circuits that have non-local connectivity. Although in general, sort of if the interactions are local to the extent that one sort of wants to explore analog simulations, that's generally kind of the native interactions will dictate what's natural to simulate. And so we're exploring this kind of opposite paradigm of native global connectivity, and then can one sort of prune this graph and have a programmable quantum system in the lab. So I'll talk about kind of two directions we've been exploring. One is how can we use global interactions mediated by light to build up programmable structures of entanglement that, for example, might be interesting as resources for sensing or eventually even computation. And then, so this is more sort of building up entanglement step by step, and then we'll also sort of explore the direction of quantum simulation, building up some non-local, some programmable interaction Hamiltonian, and exploring what new directions this cavity-mediated connectivity can take us. So here we'll be exploring applications to multi-parameter sensing. I'll give an example of taking advantage of non-local connectivity as a new probe of topological physics. And everything I'll say for most of the talk will still be in a regime where actually we can calculate what should happen, but I'll give a bit of an outlook towards trying to get beyond that regime with new hardware we're building in the lab. Okay, so broadly speaking, our group, I would say, draws on a really kind of strong track record of systems of atomic ensembles coupled to light being really demonstrably powerful for generating collective entanglement, where sort of one has some highly symmetric state that one can describe by perhaps the average magnetization and the fluctuations around it, which might be squeezed. That's been explored as a resource for making better clocks, better atom interferometers. This is all kind of still, though, dealing with a single collective degree of freedom, which is natural when you couple to a single mode of light. But in recent years, it's also been possible to sort of combine this toolbox of atoms coupled to photons with also imaging and local control, and sort of bringing those together is going to be our way of achieving programmable non-local interactions. So before we even sort of get to programmable, what do I mean by really using photons to mediate interactions? Here's a kind of cartoon for two atoms. If I start with the left one spin up and the right one spin down, one of them can emit a photon while flipping its spin down. And so that excitation that got converted into a photon can be reabsorbed by another atom. And that gives rise to some spin exchange processes that if I put in n atoms, they'll be all-to-all connected to the extent that they have uniform coupling to this mode of light. But we're going to then use some local addressing to modify this graph to also, by imaging, be able to sort of access information about the spatial structure of entanglement. And we'll also be using interactions, non-local interactions mediated by light, as a means of sort of reading out non-local observables. So the experimental setup looks like this. There's anywhere from a few to roughly 20 clouds of atoms that fill a millimeter-long region between these two mirrors. And we work in what I'll talk about today with about 1,000 actually atoms in each cloud, and that's because it turns out we benefit from the fact that having many atoms gives a collective enhancement of the atom-light interaction strength. So I showed this here as some cloud of atoms. You should keep in mind the atoms are spatially pinned, and the dynamics is going to be solely in kind of the internal states, the spin degrees of freedom. And in particular, when we want to introduce some dynamics, what we'll do is we'll send a laser field that drives a process whereby a spin can be flipped by emitting a photon into the cavity. That process won't be resonant, but there will be virtual processes where pairs of atoms can exchange their spin states. And then by combining those cavity-mediated interactions with laser fields from the side or inhomogeneous magnetic fields, this will give us a way of having spatial control. So here's an example of what an experiment in this system might look like. So here, in this case, there's 14 clouds of atoms, so each column is one of these atom clouds. But so far, we're kind of addressing them in groups. What you're seeing here is some picture where the color indicates the spin polarization on the site, and you're kind of seeing spin excitations oscillate between the left and the right subgroups of atoms here. Okay, why are they oscillating between these sites and those sites? Okay, let me tell you a little bit more about what we're actually doing here. So the cavity, the global interactions mediated by the cavity, I can write as some sort of sum over all pairs of sites of collective spin exchange interactions. And then on top of that, locally, we can also imprint some energy shift to the, so like effectively a local longitudinal field that dictates whether or not the spin exchange interactions are resonant. So one way you could get actually these dynamics is, for example, saying I'm going to have the left group and the right group to be resonant so they can exchange their spin states, and the middle group off resonant, and then only the left and right will be coupled. What we're actually doing in this experiment is a little bit fancier. Each of these subgroups has a different field, and by modulating at the energy difference between the left and the right subgroups, we can resonantly turn on spin exchange interactions between these designated groups, and I'll come back later to actually how we use this. But that's just to kind of show you visually, yes, the cavity mediates these spin exchange processes, and we have some local control of which sites interact. That, so far, you could think of in terms, you could understand that as, I told you they're individual atoms, but you don't really know whether these are just big classical spins rotating around each other. So to give a flavor, to actually start to see that there's entanglement being generated in the system, one way that we can do that is, in our particular system, we're actually working with spin 1 atoms. And one mechanism for entangling these spins is actually send in light to a system where all of the atoms start in the 0 state of the spin 1. And intuitively, that should be a way of generating atoms in either +1, -1, or might be reversed, right? Some entangled state within this spin 1 system. That has actually a long history of being studied by direct collisional interactions, but in our system, this can happen over that sort of millimeter scale array of atomic ensembles. And when we want to probe whether we're in fact generating entanglement, we can do that actually by looking for squeezing of the quantum fluctuations, right? So you might say, I have this big spin on each site that's 1,000 atoms. Isn't that kind of classical? But if you look closely enough and have good enough precision and can see that these quantum fluctuations are squeezed, that can be an indication that we're actually generating entanglement in the system and perhaps a useful form of entanglement. So here in this example, this is actually 4 clouds of atoms, but for now I'm going to ignore the spatial structure and just say I have n atoms in my cavity. I can describe them by some collective spin. That's the sum of all the individual spin 1 atoms. And because it's spin 1, the dynamics, so there's some collective fx squared that generates a twisting of the spin, an fx-dependent spin precession that kind of squeezes these quantum fluctuations. In the spin 1 system, I'm describing the dynamics on a sort of funny block sphere that has some collective spin and quadrupole moments. It turns out I will ignore the details of what these coordinates are, and it'll suffice for the next part of the talk to just think about these in the early time dynamics are well described by thinking of these as some Gaussian states, and I'll just call these 2 quadratures, right, orthogonal to the mean spin. I'll just call those x and p. As a simplified description of these Gaussian states that we generate for early time dynamics. And so by seeing that there's squeezing in this XP plane, we can start to see that there's entanglement in some form in the system. It doesn't yet tell us anything about sort of programmable entanglement, which I promised. And if you want to sort of explore, just having some global entanglement, some global squeeze state is actually exactly what you would want if, for example, you want to use this system to sense a single quantity like a global magnetic field. But there are other applications where you might want to have more spatial control. Maybe you want to localize the entanglement to individual subensembles so that you have spatial resolution. Maybe you want to do some local rotation that converts sensitivity to a global field to sensitivity to a gradient. And maybe you even want to ask, what can I do if I have more control over the graph of correlations? And in the spirit of programmable quantum systems, I'll say a bit about how do we actually program the graph of correlations between different nodes in this cavity. Kind of formally what we can ask is the question, can I use this system to build graph states, which for those of you used to thinking about qubits, right, graph states or cluster states are something you could generate by saying I have some graph where I have a CZ gate on each edge, and that will generate correlations between sigma x and sigma z on neighboring sites. Some of you might be less familiar with thinking about these continuous variables, right? I said these big spins I can roughly describe by the transverse components that I'll just label x and p. But in this continuous variable setting, there's also a version of these graph states, which is essentially that if I had a Hamiltonian that looks like xi, xj, that would generate correlations between p on a given site and x on the neighbors. So that's the continuous variable analog. And we were kind of curious, how much flexibility can we get with just this global connectivity of the cavity of generating a particular graph of correlations that I could specify by this matrix Aij, right? Even though we don't kind of turn on arbitrary pairwise interactions, it turns out if you give me a matrix of a graph that you'd like me to make, what I can do is actually diagonalize that matrix to find a natural way of building that state in the cavity. So as a minimal example, if I have 2 nodes that I want to maximally entangle, that would be an EPR type entangled state. I diagonalize that matrix that says the left is entangled with the right, and the eigenvalues, you could do this in your head, the eigen vectors are 1, 1, and 1 minus 1, right? So it's basically the symmetric and anti-symmetric modes are collective modes that I should manipulate in order to actually prepare this structure of entanglement. And it turns out that the eigenvalues of this matrix tell me which quadratures I should squeeze to make this state. So the prescription that comes out of this is if I want to make this EPR entangled state, what I should do is essentially squeeze the symmetric and anti-symmetric modes of this system in orthogonal quadratures. So that's I apply a global squeezing operation that squeezes the symmetric mode. I can now do a local rotation that actually maps that squeezing to the anti-symmetric mode. I can do any phase space rotation to pick out which is the squeezed quadrature, and then I'll do one more global squeezing operation. And now I have this state where the symmetric and anti-symmetric modes are squeezed in orthogonal quadratures, and spatially that corresponds to this correlation structure that the left is sort of maximally entangled with the right, and we've removed the internal entanglement within the ensembles. This is actually kind of a neat state because it in some form has kind of squeezing in both X and P. In different spatial modes, but there's squeezing present somehow in both X and P. So it turns out this actually can be a useful resource for the somewhat counterintuitive task of simultaneously detecting perturbations to two non-commuting observables. And I'll come back to that in a moment. But before I come back to that, just to say a little bit about, can you scale this up? The fanciest thing we've done in this system is taking 4 sites and making a square, the fanciest thing in terms of kind of provable entanglement. So that just means there's 4 collective modes that one has to squeeze in suitable quadratures. And so it's a sequence of turn on the light in the cavity, do some local rotations, repeat 4 times, and we build up this correlation matrix, this sort of checkerboard that indicates we've made this square graph of entanglement. In principle, this method does actually generalize to kind of arbitrary non-local graphs, and there's also a path to taking this beyond these continuous variables to qubits if you can have strong enough atom-photon coupling. And so this could be an interesting toolbox for making sort of richer non-local structures of entanglement. Meanwhile, though, in the lab, we were actually asking, what limits how good the entanglement is, how strong the squeezing is. And it turns out one of the limitations is actually not our ability to prepare the state, but is just how well do we detect the state. And it turns out if what's limiting you is your detection noise, one thing that can be advantageous is rather than directly try to detect this narrow sort of uncertainty of the squeeze state, use a second period of interaction to amplify that noise and also amplify your signal to have something that's easier to detect. And actually, our organizer, Emily, wrote a nice theory paper on this back when she was a graduate student in my lab, and various experiments have been done actually exploring this notion of kind of amplification or sort of an echo where one squeezes but then undoes the squeezing in order to better detect the signal, right? So the picture here is this displacement in green is what we're trying to detect. In order to detect it, rather than directly detecting here, one could either reverse the Hamiltonian, or in our case, for these Gaussian states, we can equivalently do a 90-degree rotation, and then apply those same interactions to kind of unsqueeze. And that makes it easier for us when we're detection noise limited to get the most out of the state that we've prepared. So here we get about a factor of 7 dB enhancement. And one fun thing, though, in this system is we can do this, let's say, for the symmetric mode of all these ensembles, but we can also now generalize this to be able to sense a spatially patterned field. So if I add some additional local rotations, I squeeze, I map the squeezing from this, what I call the k equals 0 mode that's sensitive to global displacements, to the k equals pi mode that's sensitive to spatially oscillating fields. I can take this protocol and use it to actually have this a spatially resolved sensor that I can optimize for a given, for sort of putting the entanglement in the mode that's sensitive to the signal I want to detect. So in this case, for example, sensitive to an oscillating field. So that kind of, I think, opens a number of directions where we would love to kind of explore if you go beyond just saying I'm trying to detect a known field, but maybe I'm trying to do a more sophisticated task like classifying spatial patterns. Is there some set of modes that's optimal to squeeze to help you do that task? It also sort of, I mentioned earlier, this notion of having kind of entanglement in 2 conjugate quadratures, squeezing in 2 conjugate quadratures. And that could be interesting as a resource for going beyond sort of sensing a scalar quantity to sensing vector fields. And another exciting direction that we would love to explore is actually a proposal that our previous speaker, Robert, is involved in, which is showing that actually these EPR entangled states can actually be a resource, somewhat surprisingly, even these Gaussian states, for getting exponential speedups for certain tasks that involve sampling from sort of spatiotemporally correlated noise. And so roughly the story there is that if you have kind of an array of EPR pairs, I'm going to think of sort of half of each pair as my sensor and the other half as some reference that's unperturbed. Maybe I'm sensing magnetic fields, and these are in magnetic field insensitive states, or they're far away. But then you can ask, in these sensing modes, can I simultaneously get sensitivity to displacements in X and P. In other words, can I detect that there's a displacement of some amplitude without knowing what direction it's in phase space? And in principle, the EPR type entangled state lets you do that. And the reason it lets you do that is basically there's no uncertainty relation between the sum of the X's and the difference of the P's. That's why you're allowed to have kind of squeezing in both quadratures. And so if you know that subsystem B is unperturbed, there's no limit on how well you can detect changes in X and P in subsystem A. So that's kind of how this is a resource. Now, just because these two quantities commute doesn't actually mean that you have a good way of measuring them both simultaneously, right? So in principle, they're measurable, but these are non-local quantities, right? So do we actually have a good way of measuring these non-local observables? Well, it turns out a cavity is actually a good tool for measuring non-local observables. The way we do it, and this was an idea by my student Eric Cooper, was to say, let's actually use this trick of interaction-based readout, and now we're going to amplify both of the observables we want to detect. So we're going to have this EPR state that gets displaced by some unknown, in some unknown direction in phase space. And in order to detect both the change in X and the change in P, we'll first amplify the symmetric mode. That's the one that was squeezed in X. We'll amplify that one in the X quadrature. And then we'll amplify the antisymmetric mode, the one that was narrow in P. We'll amplify that in the P quadrature. And so now we can actually just read out in this 45-degree basis. We already have a big signal, so it's okay that we're kind of only getting half the information from each of X and P. We can read out in this 45-degree basis, and this now gives us information about both the sum of the X's and the difference of the P's. And now it turns out from our signal that's in this sort of in-between quadrature, we can reconstruct this sort of, complex number that tells us our displacement in any direction in phase space. And the green circle is, without entanglement with this reference system, how well could you do? And what we find is that in terms of phase space area, we're about a factor of 2 below the best you could do without this EPR entanglement, so without the entanglement with the ancilla, in terms of simultaneously having sensitivity to changes in two orthogonal, two non-commuting observables. So that's that's just now with kind of a, physically there were 8 clouds of atoms, but they were entangled just in 2 subsystems. But if one can kind of scale that up and have arrays of EPR pairs, this is the direction for actually potentially getting an exponential speed up, and that would be exciting. Okay, so kind of a key ingredient that we used here was this notion that the cavity lets us access non-local degrees of freedom. And another place that we thought it would be maybe fun to kind of explore that cavity as a non-local detector is in the context of topological physics. So I want to tell a story about that, but before I do, I'm going to introduce a bit more the toolbox for how we go from programmable entanglement to more kind of programmable interaction. So I want to simulate some Hamiltonian with a graph that I can program in. And roughly speaking, from what I told you before, I gave you this picture that the way I can kind of build up a graph of entanglement is by having the cavity sequentially couple to different collective modes. They're eigenmodes of that graph. If my graph is translationally invariant, which is one common case we might be interested in, then the natural basis of collective modes are actually just spin waves. And so the picture you can have in mind is actually if I apply a magnetic field gradient, then what was the k equals 0 mode will be a different momentum mode at a different time. This gradient cycles through different spin waves in the cavity, and by sort of changing the intensity of light versus time, as I'm cycling through these different modes, I can actually engineer the dispersion relation for spin excitations in my cavity. That's a momentum space picture, but I can Fourier transform that, and there's maybe an even more intuitive picture, which is to say, in this setting, the spectrum, the frequencies present in my drive field, are going to govern what couplings are present versus distance in my array. So the picture is in this gradient. I can basically, the resonant spin exchange is turned off, but by having a pair of frequencies in my control field, I can turn on spin exchange interactions at a particular distance that matches kind of the difference in Zeeman energy between sites at that distance. So that's an example of sort of turning on, building up correlations at some particular distance, in this case, a distance of 10 sites, just by specifying a particular frequency difference in the spectrum of my laser. Okay, and so by then adding more frequencies into the laser field, you can build up, it's sort of easy to have an arbitrary waveform generator control the modulation waveform of the laser, and then we can sort of build up various graphs of interactions. We can control also the sign of the interaction by the phase of the waveform, the phase of the modulation at each frequency, and so this is a pretty flexible toolbox. So this is an experiment we did already a few years ago, and now one of the things we've been curious about is, can we use this toolbox? We can program in the couplings versus distance. We also have this non-local readout. Maybe this would be a nice toolbox for some studies of topological physics. And so what was kind of the motivation there? I think in the big picture, like what I find exciting is this idea of topological phases in principle give us some way of encoding information robustly in non-local degrees of freedom, but precisely because you've stored information, non-locally, it's hard to access. Wouldn't it be nice if you can use a cavity to controllably access some non-local observable? So this is kind of an idea that's been out there for a long time, and we're going to do sort of a very minimal version of this. So first we need a way to kind of engineer some topological system in our cavity, and there's a couple of approaches you might take, but the one that we took is to say, let's use this ability to kind of program in the couplings versus distance in our lattice. And specifically, so the mapping I have in mind is these spin exchange interactions. I'll think of these spin excitations as particles that can hop between sites of the array. And there's actually a number of ingredients we have. So I said we can control the hopping amplitudes and principal phases. We won't use the phases yet. We can decide whether or not we, connect the ends of some chain. And we'll also be able to actually tune the on-site interaction, which is just the spin exchange interaction within each ensemble. We're going to do a very minimal test case of a model, kind of what we asked, what's the simplest model of topological physics we can build? And we decided to build this SSH chain. It's already a bit fancier than the translation invariant things I showed before. We actually need to not just use a linear magnetic field gradient, but we have some staggered effective field that we imprint optically, and then two different frequencies turn on the couplings in this dimerized chain. And if we want, we can connect the ends with a third frequency. So in the system with periodic boundary conditions, I won't say too much about the details of this except to say we can measure a topological invariant called the Zach phase, which either winds or the relative phase between the A and the B side either winds or doesn't wind as a function of momentum. That changes as we expect, depending whether on this dimerization, so the J prime relative to the J. And then a second sort of signature of the topological phase are edge modes. One should, if you initialize sort of excitations on one end of the chain, see them oscillate between the left and the right edges. It turns out to do that, that should happen in a non-interacting system. And actually for us, it's not trivial to have the non-interacting system, but so we developed a trick to actually have a tunable interaction in this system. So the trick is essentially we have this ability actually to zero the on-site interaction by turning on two fields, a red detuned drive field and a blue detuned drive field, which are chosen so that if they're equal strength, their effects are actually going to cancel. So the on-site interaction will cancel. The hopping would also cancel, except that we can attach a phase of pi to the hopping of, let's say, the blue sideband compared to the red sideband, so we can make the hopping terms add and the on-site interactions cancel, and then by tuning the imbalance, we actually have a tunable interaction in this system. Okay, and in the experiment I showed before, we're sort of driving with this crazy waveform that corresponds to building that SSH chain with a tunable interaction, and then we can also ramp on the couplings adiabatically if we want to prepare the ground state, or we can look at dynamics. And so if we look at dynamics in the system, the way this might look is we initialize some spin excitations on the left edge, we turn on our SSH couplings, and we see them oscillate. This blue curve is in a non-interacting case, seeing them oscillate from the left to the right and back. As we turn on interactions, this oscillation actually gets suppressed. It turns out one way to understand the suppression is actually to say, well, in the limit where the edges are well separated from the bulk, this looks kind of like a two-site Bose-Hubbard model. And with no interactions, I just get these oscillations, kind of essentially Rabi oscillations between left and right. But if I turn on interactions, there's a known effect in this two-site Hubbard model of self-trapping where the interactions get localized to one edge. And so that's kind of a picture for the oscillations stopping. And there's kind of a richer picture if you ask what happens if I visualize not just the population imbalance between the two sites, but also the relative phase. And what one expects is that initially there's this single fixed point for no interactions where I get this Rabi dynamics oscillating between left and right. But if I turn on interactions, for strong interactions, the fixed points would be up or down, so all excitations left or all excitations right. And we can actually have a way of directly mapping out these dynamics of the phase and not just the population if we use, can I have 2 more minutes? If we use the cavity as sort of a non-local interferometer, where we initialize the spin excitations on the left, turn on a coupling between left and right, evolve under this SSH Hamiltonian, and then sort of have another beam splitter, which is this non-local coupling between the edges of the chain, and measure the imbalance. And this lets us actually map out not just the population dynamics, but also the relative phase between the edges in a way that matches this picture. So this was starting to use this kind of non-local cavity-mediated interaction to probe the non-local edge modes. This is so far mean field dynamics, and I think it gets most interesting if one starts to go to a more strongly interacting regime. So in the last minute, I'm going to skip over some prospect for measurement-based preparation using graph states and measurement to prepare states with an entanglement structure that's connected to holographic duality. So that's a story that you can ask me about later. This is some theory. And I'm just going to say one more thing about kind of what are we doing to try to get to a more strongly interacting regime. So in kind of next generation experiments, there's kind of 2 directions we would like to go. To have actually single atom qubits, right? So that you have each site is a strongly interacting, hardcore boson, or perhaps a qubit that can have at most a few excitations that you can individually detect. So one direction is kind of building a better optical cavity. And there's a figure of merit for how coherent the interactions can be, which in the best optical cavities, this number is somewhere in the hundreds. But there's another direction we're going. This might sound good, but to get the coherence of a pairwise interaction, you have to actually take the square root, and then there are some numerical factors that hurt you. So it's really hard to have coherent interactions between pairs of atoms in the optical domain. So we've recently also built a millimeter wave cavity. So this is actually a superconducting cavity. It has to live in a cryostat. It couples to transitions between Rydberg atoms. And based on the measured finesse of this cavity, this should boost this cooperativity figure of merit to upwards of 1 million. And also, because the wavelength is millimeter scale, there could be room inside here for sort of large 2D atom arrays that could talk to each other via the cavity. So you can read about the technical side of that experiment here. This is just to say, so far we don't yet have Rydberg atoms in the cavity, but even actually the local dipolar interactions between Rydberg atoms themselves are quite strong and long-ranged, and there's, I think, a possibility of extending some of the Floquet engineering techniques I introduced to dipolar interacting systems. So these are sort of first experiments with a dipolar Rydberg atom array in our lab, and we're excited for the possibility of combining that with strong coupling to photons in this millimeter wave regime in future experiments. Okay, so with that, I should wrap up and just thank the team who did these experiments and take any questions.
Yeah, thanks for the very nice talk. For the topological physics, maybe a naive question. So the fact that there is a cavity that potentially can address the system globally, like, do I still expect the topological protection in that case, or do I still expect the edge modes to be robust?
In some sense, I've so far thought of it as there's kind of two, there's kind of 2 different steps to this. One is I use the cavity to simulate a Hamiltonian, and at least so far I'm thinking of this abstractly as now I've built that Hamiltonian, and then separately, and by itself, if it has the correct symmetry, I guess I would expect the topological protection. And And then the second step is kind of using the cavity to probe the system. And that allows me to then add in this non-local element.
Yes.
Does that kind of make sense?
Yes, that makes sense.
And I think that's kind of the point, is that you can kind of, you could also imagine building the topological system differently, right? That I have a Rydberg atom array and local interactions, and I prepare some, toric code state or something, and then I want to measure some non-local string operator or manipulate it, and the cavity is responsible for that. That's kind of like a dream with this like next generation setup, right? That I use an ancilla atom and talk to some string in the array, and that's kind of the direction this can go. And so the cavity may or may not be involved in preparing the topological state or the Hamiltonian with the topological band structure. There's sort of two separate parts, and for now we used it for both.
Right.
But there's different options.
This is perhaps more like a theoretical question even, or like,
yeah.
I don't know, maybe a philosophical question. Like, if one wants to use a cavity like simultaneously both for like mediating long-range Hamiltonian interaction and also for like, let's say, efficient readout, the fact that there are dissipative like channels that are also non-local, like how does that affect the topological physics?
I think it's a really great question. One thing I'll actually point to without fully answering the question is there's some recent work by Ash Clerk, which I have yet to look at more closely, but it actually looks at a system very much like ours, an array of atom clouds and some programmability. And they actually think about dissipative stabilization of topological states. So like an AKLT, like SPT phase in this dissipative setting. And so I think this is an interesting direction to actually ask, so far I've kind of talked about doing our best to make things coherent and ignore the dissipation. But another and it's not a terrible thing to do, because once we've prepared some state, we can turn the light off. So we don't really need steady state entanglement. But I think it's nevertheless an interesting question to ask, how do you engineer the system to naturally give you like steady state entanglement? And this paper might be relevant to addressing your question.
Thanks.
Yeah.
Just two questions, Monika. Can you go back to the topological for the site model? So where was the strong bond and where the weak bond? I was a bit confused by your sketch.
Oh. Well, I
just
guess
maybe the next one.
I think in my sketch I just
not just the next one.
I was just labeling.
The four, no more further.
But yeah.
This one.
Oh, in the actual so if J prime is less than J,
okay,
that's where I'll see the edge states oscillating. Maybe it doesn't look like it in the sketch. Yeah.
Yeah, I was a bit confused. Yeah. Did you actually check whether the oscillation frequency actually or then changes with the length of the chain? Could you go for more than 4? Yeah.
So we have played a bit with 6, but it's hard. So, because it slows down, right? So we can, So I would say we actually still checking, can we maybe clean things up and get to 6 and still probe it? But yeah, it's a good question. Yeah.
All right.
Yeah.
Yeah, that's also what I'm curious about, how the oscillation changes as a length. But anyway, I have another question. That you do not have an exact control over the atom number per cloud.
Yeah.
So how you will be able to cancel out the on-site interactions, maybe, because the on-site interaction kind of depends on the number of atoms per cloud. Oh, no.
Oh,
yeah.
So there's kind of, I think, two ways you could get an on-site interaction. Mm-hmm. So one is just like if I have let's say I have a very small number of atoms, then like just I'm sort of making some Holstein-Primakov approximation, and if I break that, the next order term can correspond to an on-site interaction. And then even in sort of the limit of a large number of atoms per site, there's this like spin exchange mediated by the cavity, which can also happen between 2 atoms on the same site. Mm-hmm. And for us, when I talk about tuning the on-site interactions, I'm tuning that like on-site spin exchange, and that one we can tune to 0. Now, in principle, there's still some nonlinearity from the fact that this is actually a sphere and not, right? Like there is a finite number of atoms. That effect is still small enough that it's, I think, not an effect in.
Maybe I misunderstood the Hamiltonian, because in a Hamiltonian with the on-site interactions, it's NJ inside, right? Is NJ the number of atoms in that cloud or something?
Sorry, I wanted to go back to.
Yeah, this one. The last term.
So this is referring to the number of spin excitations. And it is true. So in some sense, like what we're looking at is in the end mean field dynamics, and it's true that this mean field interaction strength actually does depend on the number of atoms in the cloud.
Yeah.
And so we do our best to balance that. Yeah, the cancellation is kind of independent of that when we tune it to 0. And then, but it's true that like disorder in the number of atoms per cloud would result in disorder in the couplings.
Yeah, I see. Thanks.
Yeah. Mm-hmm.
Hi, thank you so much for the good talk. I had a question a little bit earlier when you were talking about measuring the entanglement. Has there been thought about how you may be able to extract something like the entanglement entropy or some Reddy entropies when you separate these ensembles? Yeah,
so it turns out actually for Gaussian states, one can efficiently determine the entanglement entropy from correlations, just measuring correlations in a small number of bases. I think it's, the number of bases is maybe linear in the system size. So it scales in a favorable way, or maybe only logarithmic. Someone here probably knows. But so anyway, so I can measure correlations in a few different bases and efficiently in principle reconstruct the entanglement entropy. And that's something we actually would love to do. And I sort of blew through a slide on something we're thinking about, which involves measurement-based preparation of states with an entanglement entropy that matches kind of a CFT prediction. And the sort of idea there would be for Gaussian states, this is something where one can, in principle, efficiently actually determine that in the experiment. I think the biggest challenge is actually just having good enough signal to noise and doing it even in sort of for complex graphs still,
Is this like a random measurement protocol or just measuring every single possible correlation function?
What you need to know, you'd like to reconstruct the full covariance matrix. So I want to get all of the correlations that look like, xi, xj, xi, pj. But actually, like the number of measurements you need. So there's still, I think, going to be in the end to get like good enough signal to noise. There's probably something where the number of measurements will scale exponentially with the system size, I think, to get good enough signal to noise is my instinct. Somebody in the audience, again, might know this. But at least in principle, sort of, you don't need a lot of different bases to get, right? I can measure all the X correlations, all the P correlations, and then I can do a few different sort of local rotations to get XP correlations between any pair. And then it's just a question of, do I have enough statistics to actually get low error bars on that covariance matrix. Once you have that covariance matrix for Gaussian states, you could reconstruct efficiently.
Thank you.
Yeah.
Hi, Monika. Very nice work on these graph Hamiltonians. I was wondering if in the spirit of holography, can you start generating terms that go beyond quadratic terms, like cubic or something more?
The interactions that go beyond quadratic terms?
For example.
Yeah. So actually, there's been some recent work by James Thompson showing how to generate three-body interactions in this type of collective spin system. So, I don't know, F plus, F plus, F minus, and four-body as well. I have always been afraid of that direction because somehow intuitively it happens at higher order in perturbation theory, and you might think that like the dissipation is going to be worse. But I'm not quite sure whether that's actually true, and I know there's ongoing work by James Thompson and Anna Maria Ray thinking about this, and it's definitely an interesting direction. The other approach I can imagine is kind of in our dream of our atom array in this strongly coupled millimeter wave cavity, you can kind of think about having some ancilla atom that talks to groups of atoms and mediates multi-body interactions. So those are things I'd love to explore in the future.
Thank you.
Yeah.
Okay, so let's thanks Monika again.